All right, so earlier we saw how to use timers as output output compare mode. In this video, we'll do an extension of the output compare mode into something called a pulse width modulation. Okay, so the setups are somewhat similar. We're still going to be using timer 4. We'll still use the channel 4 of the timer because we already know we can see certain things happen on the blue LED that's connected to our discovery board. For that reason, we're choosing the blue LED, which is on port D pin 15, which happens just to be connected to timer 4 channel 4, as we saw last time when we were talking about output compare. So pulse width modulation, what does that mean? If anybody's ever used an Arduino, and I remember quite a few of you said you had at one point, there is an Arduino function called analog write. The analog write function, what it does, if you really look at the analog write output on an oscilloscope from the Arduino, you don't really get an analog value. What you get is a digital waveform which goes high and low, and the analog voltage is proportional to the amount of time that waveform stays high with respect to the overall period of that waveform. So for example, let's say I'm running my Arduino at 5 volt. Setting a analog write of 128 in Arduino basically means I want to write half the voltage, 2.5 volt, at a particular analog pin. When I do analog write with 128, what I end up getting at the output of the Arduino is basically a waveform that looks like this, where it stays high for half the time and low for half the time. That is called a 50% duty cycle. If I change that value to 64, because 255 is the maximum value you can write an analog write in the case of the Arduino. If I write a value of 64, which happens to be what, 1/4 255, then we'll see a 25% duty cycle waveform like this, which means 25% duty cycle basically means stays high for 25% of the overall duration of the waveform. So the duration of the waveform is this period right here. 25% duty cycle means it's high for that amount of time. So this particular kind of signal, where you can use a digital signal as a proxy or power proxy of an analog signal, is called a pulse width modulation. Okay, so we're basically changing the width of the value, or the average value of the analog waveform, by changing the width of the pulse width, and we're modulating that to get the different analog values, and hence the name pulse width modulation. PWM is nothing more than what we have already seen in terms of output compare earlier using timer 4. In the earlier example with timer 4, we basically turn on and off an LED at half the rate, high for half the time, low for half the time, high for half the time, low for half the time. That's basically what we had set up, was a 50% duty cycle. Right? Using, just by comparing the values at what was stored in the capture, what we had initially loaded in the capture compare register, with what the current count of that particular timer was. In the case of the pulse width modulation, okay, PWM, the similar setup is very, very similar to output compare, and you'll see when you look at the procedure. The PWM mode is described in section 18 of the reference manual for STM32F407. Here is a copy of that. It says it allows signals with a particular frequency determined by the value of time ARR register. Well, we knew that, right? In the past, we basically used ARR and the prescaler as a way to set the overall period, or the frequency at which we get an update event. Well, in this case, we're going to use the ARR register to set the overall period of this waveform. What do we mean by the period of the waveform? This thing right here. So if you look across all three pictures right here, they have the exact same period. From this high pulse to high pulse, this high pulse to high pulse, and this high pulse to high pulse, the value is the same. So that is set by setting a value on the ARR register. That's what it's saying. And a duty cycle is determined by the value of the capture compare register settings. So this 50%, if I wanted a 50% duty cycle, in this case now, in the output compare, remember we said as long as the CCR4 value is less than ARR, we were going, and we set the thing to a toggle mode, we would get equal high and equal low time. In this case, we get a control, and the way we control it is by using the PWM mode, not the toggle mode, PWM mode on channel 4. The period of the waveform, this period of the waveform is set by the ARR register, and this high part of the waveform, called the duty cycle with respect to the period, is done by setting the capture compare register. So if I have CCR as 500 and the ARR as 1000, that's CCR is half of 1000, so we get a 50% duty cycle. If I have ARR as 1000 and the CCR register as 750, I get 75% duty cycle. Similarly, if I have CCR as 250 and the ARR as 1000, I'd get a 25% duty cycle. And I could, depending on what I want, I can set whatever duty cycle I want. That's the basic premise of the PWM mode. It says the PWM mode can be selected independently on each channel. So remember there are 4 channels. By writing a 110 or a 111, PWM mode 1 or 2 in the OCM bits in the CCMR register. Well, recap, port D15 is connected to the blue LED. Blue LED is connected to timer 4 channel 4. Timer 4 channel 4, that means we need to write to capture compare register 4, and that can be compared with the current count. Okay. It says by writing a 110 or 111 on the output compare mode bits of the time capture compare mode register, if we write a 110 or 111 here, we are enabling the PWM mode. Okay, how does this all work? Well, here is my ARR value and the CCR value I set. I let the counter run. This is what happens. So the counter is counting up. By default, I start at high level. When I hit CCR, that pin is going to drive low until I hit ARR. Okay, and at which point I'm going to stay high again. And then when I hit CCR, I'm going to go low. And I'm going to stay low until my timer overflows, at which point I go high again. So basically, if I had CCR down here, it would have a low, small, high pulse. If I have a CCR above here, right here, it would go up to this point. That means I would have a really big high pulse. So the period is dictated by the ARR register, and the pulse width is dictated by the CCR register. Okay, when we generate the PWM. Okay, how do we? Here's an example from the reference manual showing count register is 8. So this is telling me that the ARR was set at 8 because this count register goes up to 8 and resets to 0. Now if I had CCR set to 4, then this is the output reference. So that's the output pin I'm looking at right here. It's high until I hit 4, at which point I go low, and I stay low until 8, and at which point I reset back to high. Right? If I have set CCR equals 8, then I go high, a giant dip, a small dip, and then go back. Okay? If the CCR is set to greater than 8, then of course I always stay high. Okay? And if I have CCR set to 0, that means I never go high, and I stay low the whole time on that pin. Okay? The IF is the flag that tells me when I've reached that value of CCR of the counter getting to the CCR value. Okay. All right. How do you do this? This is the procedure that's described in the reference manual. It says select the output mode by writing CCS bits and CCMR register. Select the polarity. Select the PWM mode, 1 or 2. Program the period and the duty cycle. Set the preload bit in CCMR register and the ARPE bit in the CR1 register. Select the counting mode. Remember we talked about either you could do up count, a down count, or you could do a center align mode, center align count mode when we talked last video about timer output compare. And then we enable capture compare, enable counter. If you look at these steps, some of these setting of the bits are very similar to what we did in the output compare. So let's actually walk through the steps and go through the process of trying to see if we can generate a pulse width modulated signal on timer 4, channel 4, which we can then see as change in brightness in the blue LED. Okay, so let's go ahead and do that. So let me open up a Kyle Microvision project. So I've created a Kyle Microvision project with a blank main.c file. So here it is. And let's follow the steps outlined in these steps that are outlined in the reference manual on how to set up a PWM. But before I do that, let me include the header file. So I have my header file included right here. Okay, included. Let me define the LED blue as pin 15. And then let's go ahead and let me also define some values, like define the period as being, let's say, 10,000, and let me define duty as being 5,000. We can just change these values here later on and play around with the duty cycle and so forth. Okay, step 1. Well, all of this, again, these steps that are outlined in the reference manual assume a few things. 1, that you have enabled the timer. 2, that you have enabled the GPIO port. So let me basically, since this I said that it's very similar to the output compare, here's my output compare. Let me go and copy the enable of the port D as well as a timer 4 enable in RCC. So we've enabled the clocks for the GPIO-D and the timer. Next thing we need to do is, just like what we did when we did output compare, port D pin 15 is connected to timer 4 channel 4. In order to do that, we had to go and set the AF2, port D pin 15 mode register to alternate function mode. So let's go do that. Set alternate function mode on port D pin 15. And we want to select, just like what we did in the output compare code, we want to enable the AFR alternate function register high bits so that we are assigning port D pin 15 to timer 3 through 5. In our case, we're using timer 4. Okay. We do want to set, so now let's go and see what we hear. Select the output mode by writing CCS bits in CCMR register. So let's see, what does that mean? All right, so this is my PWM code. I'm going to move my output compare code out of the way for now. All right, it says write to CCS bits 00 sets the output. Well, that's a default. We can just let it be, or just like what we did in the output compare compare code, we can just clear it just to be safe. So I'm basically copying that as well from the output compare portion of it. So selecting the output mode by writing the CCS bits. So we've written the CCS bits. Next, select the polarity by writing the CC4P bit in the CCER register. This basically says whether the channel starts out at high or the channel starts out at low. In other words, in this picture right here I had, notice when I enable the count, when it counts, this output pin starts at high and remains high until I hit CCR, and then it goes low. That's active high. That's what it says we can do. We can choose. Okay, so by choosing the capture compare output polarity active high, that's what we mean. So we can leave that as 0 as well. Okay, so let me go and let me go and where's my timer PWM. Okay, so output mode is set. Select the polarity by writing the bit in the register. It says select the polarity by writing the CCPX bit, and basically that's saying set that equal to 0. So by reset, that's a default value. We can let's go set this up regardless. ER, what are we doing? CCER register and equals not times CCER. This is the CC4P bit. Okay, so basically we're setting it to a low. So we're clearing that bit so that it's all right. Next step. So we've set this capture compare register. Next, select the PWM mode 1 or 2 by writing in the CCMRX. Right, so on CCMX, if I write 110, we have a PWM mode 1. That means in upcounting mode, it's active as long as the timer counter is less than CCR1. So what I showed you in that picture where it says high until the CCR, that's PWM mode 1. So we want to set that as 1. So we want to write a 110 in there. When we did the output compare register, this is what we had written. So I'm going to copy from there. All right, so right here. Okay, so this was setting, so I need bit 110, so the third bit, second bit need to be a 1. So bit number 2, bit number 1 need to be high to set PWM1 mode. Right, so let me just add that comment from what I have on my slides here. Select the PWM mode, so that's what that was. CCMR2. Okay, next we need to program the period and the auto ARR register. Okay, so for the period, next step is program the period and the duty cycle respectively in the ARR and CCR registers. So ARR is the period, and so step 3, let me copy the actual comment from the reference manual. Program the period, right? So I need timer 4 prescaler. Okay, let's just divide. Let's just get for now. Let's just get the same prescaler that we had before. That means that the counter is now running at 1 kilohertz. Let's set the ARR register to 100, and we'll set this to a 50 for now. Okay, so 1 kilohertz, and then I'm going to count to 100, and then it might be, we'll see what the frequency is, and then deal with that. All right, so this is the period, and in the CCR register is where we would put the duty cycle. Right, these are defined as pound defines right here on top. Oh, duty. I call it duty. So period and duty. So we'll change. Okay, we'll change this up top every time to see how that affects the duty cycle and so forth. All right. Next, set the preload bit in CCMR and the ARP bit in CR1. Preload bit. So let me copy that comment. Set the preload bit in CCMR. So time for CCMR2 preload bit. So CC4PE preload is CC4E preload bit 11. So we need to set that, and the ARP to 1, 2. So bit 11 and 7 in CR1 and CCMR2. Okay. 1. Okay, in CCMR1, CCMR, we're setting this bit. Timer CCMR2 OC4P. All right, and then in CR1 we're doing timer CR1 ARPE bit. Okay. Next, select the counting mode, PWM edge align. So we want to say edge align, counter runs up or down, and then we want to say the up counter, so 0, 0, 0. So it looks like that's all default if we want to leave it as is. Okay, leave default, so we can just leave everything at default there. All right, so and that will set this kind of PWM signal. So up counting PWM signal. Right. So I'm gonna just copy the comment up here and say leave it as a default. Leave the default. Direction is 0, up count, CMS is aligned, or you can really write to it if you want. All right, next, what do? We need to enable the compare CC4E and then enable the count. Enable the compare, capture compare, and enable the counter just like before. And let's see, that's the same from output compare as well. And the last thing we do is that, and we just sit on while one. Okay, I'm gonna build this code real quick. All right. No warning, blah blah blah. One warning generated, warning no new line. Okay, that's fine. It's talking about this. They needed a new line. Let me build again. Okay. All right, everything looks good. All right. So what we're gonna see now is that by changing these values, we should be able to see a particular duty cycle. So I'm gonna just hit run that and open my debugger right here. I'm sorry, my logic analyzer. I'm gonna hit run. Right now I see nothing. I'll press reset so that the code is loaded. And there you go, it's running. All right, we stop, and I see that I have a 10 hertz signal. I have a 10 hertz signal, so the frequency of the waveform is 10 hertz. You can see that the duty cycle is close to 50%, 49.5 it says. So the duty cycle is close to 50%. Okay, and I keep this running for now, and what I'm seeing is that my blue LED is flickering quite a bit. Now I go to 25%. Okay, so it's going to stay on for 25% and off for 75% of the time. And I'm going to, again, start this and press the reset button. And did I load? Oh, I built it, but I didn't flash it yet. So I'm going to flash it and hit run. And I should see this in the capture code that I'm at 25%. 25% duty cycle. And I can really see it flicker. So I want to change my frequency so that I don't see it flicker that much. So I'm going to just change that to 1599 for now. So that'll be 10 kilohertz. And I'll make it 1250. Load my flash, hit run. I can still see it flicker. So we need to play with my frequency here a little bit. And I think I'm running at 40 hertz right now with a high of 25 and a low of 75% of the time with a duty cycle 25%, that means. Right. Let me go change this. To 125. Let's see what happens. So now I actually don't see the flickering. I just see that the LED is lit up fairly low. And if I go look at my logic analyzer again, I'm going to run it. So I see 25% duty cycle, much higher frequency. So higher frequency, so 400 hertz. I'm seeing 25% duty cycle, and then I noticed that when I look at my blue LED, it's lit up, but it is not as bright. So let me change this to 75% duty cycle and build the code again and flash the code again. So I'm going to run it, and here if I just have it run and I hit reset, and I should see a 75% duty cycle, and when I look at my blue LED, it looks a little brighter than before. Okay, and 75% duty cycle in my analyzer, I also have an analog voltage. So if I run this, so it's telling me that I'm seeing 3 volts on that line. Okay, 3 volts. If I have 100% duty cycle, close to 100%, so let me go put this as duty cycle is 99. So this would be close to 100%. So I should see the output to be, let's see, I believe the power on this is 5 volts. So we'll see. Okay, so I built it, and I'll flash it, and I'll look at this, and hit reset. Okay. Okay, what I notice is that I'm staying at 99% high, 98% it says. There you go, 98%. And then low for the remaining 1% or so. And I am at a voltage 2.9. Oh, so the overall voltage is 2.9. So the output channel must be close to 3 volts. And this is saying 0. And yeah, that's true. The analog output and the line is 3 volt long. So this is saying it's 2.9 volts for that month's amount of time, and then 0 for the remaining. So it's not quite what I was hoping I would get for analog. So, all right, so that's pulse width modulation. And your job this week is going to be to use that PWM to drive a DC motor.